Hello, my name is Ryan Gary Kim. On behalf of me and my colleagues at Washington State University and Carnegie Mellon University, I am pleased to present this overview of our article, Wireless NoC for VFI-enabled multi-core chip design, Performance Evaluation and Design Trade-offs. As the number of cores packed into a single chip rises, scalable power management strategies are needed to maintain reasonable power budgets. Voltage frequency islands, or VFI, presents one such method. In VFI-based designs, the system is partitioned into islands, which then adjust their voltage and frequencies in order to reduce the power within allowable performance penalties. However, a main challenge in VFI-based designs is the communication cost. In typical benchmarks such as Splash and Parsec, communication remains predominantly long distance. This long distance communication has a negative impact on the application performance. Also, as with any other multi-voltage or frequency design, voltage and frequency translators must be placed at the boundary of each VFI. These inter-VFI interfaces increase the communication delay and makes inter-VFI communication costly. In this work, we tackle these issues through two innovations. The first of which is through the VFI clustering methodology. Here, we propose the use of a hybrid VFI clustering that combines both utilization and communication-based clustering. This allows us to minimize inter-VFI communication without greatly increasing the intra-cluster utilization variation. Secondly, we utilize the Small World Wireless NoC, or mSWNoC, for VFI-based designs. These mSWNoCs are characterized by their small world connectivity, which reduces the hop count and average communication costs, and the wireless long-range shortcuts, which we utilize for the costly inter-VFI traffic. We then modified the mSWNoC architecture in order to support VFI-based designs. The mSWNoC creation is separated into three steps. Intra-VFI, in order to fully connect each VFI and ensure that all inter-VFI traffic remains within the VFI. Inter-VFI, in order to connect the VFIs together and allocate bandwidth appropriately. And wireless placement, in order to add wireless shortcuts for inter-VFI communication. Below, we show two examples of wireless placement that we evaluate. Minimize hop count, which reduces the average hop count, and maximize wireless, which increases the wireless utilization. More details of these techniques can be found in the paper. In this work, we present our full system findings based on traditional NVFI or non-VFI mesh-based systems. Here, we can see that the wireless plus smaller connectivity is able to mitigate most of the performance penalties introduced by VFIs. For some benchmarks, we are able to actually outperform NVFI mesh, Canio, FFT, Radix, and VIPs. Also, by implementing both VFIs and mSWNoC, we are able to save significant energy delay product over the traditional NVFI mesh systems. In conclusion, we have seen that VFIs are a scalable power management strategy and an enabler for energy-efficient multi-core design. By using the mSWNoC topology, we're able to provide an efficient communication backbone which can be tailored for VFIs. To the use of both of these paradigms, this article presents a platform which is able to save significant EDP with little performance penalties. Thank you for listening, and we hope you enjoy our article.